Assalamualaikum, selamat siang dan terima kasih kepada Bapak Ibu yang telah menghadiri acara webinar kita pada siang hari ini. Perkenalkan, saya Zulfikri, Bisnis Direktur PT Testindo. Saya akan mendampingi Anda sekalian selama webinar ini. Kita akan punya 3 sesi presentasi dan 1 sesi tanya jawab. Webinar evaluasi dan monitoring struktur jembatan dan struktur bangunan gedung dengan model updating. Saya akan didampingi oleh engineering saya. Pertama, Pak Lukman Murdiansyah, STMT. Beliau S2 di ITB tahun 2013. Beliau bridge engineer kami. Bertanggung jawab untuk desain dan analisis struktur, terutama jembatan. Kalau ada Pak Rian Kurnia, beliau S1-nya UNAN, S2-nya University Teknologi Petronas di Malaysia. Ketiga, ada Ilham STMT. Pak Ilham adalah struktur engineer kita untuk desain dan struktural analisis. Beliau S2-nya di ITB. Yang keempat adalah Mr. Eddie Dascott, dan beliau adalah General Manager Dynamic Design Solution, prinsipal kita untuk FEMtools. Baiklah, izinkan saya perkenalkan perusahaan kami. Mungkin beberapa dari teman-teman adalah di sini adalah baru mengenal Testindo. PT Testindo adalah perusahaan berlokasi di Jakarta Timur, Jalan Raden Inten 2, nomor 62, Duren Sawit, Jakarta Timur. Kita mempunyai skop bisnis di bidang trading sebagai distributor produk-produk dan juga sebagai services dan konsultan. Pertama kita distributor dan menyediakan produk tester, alat uji. Yang pertama destructive tester, alat uji merusak seperti uji di laboratorium atau uji merusak di lapangan juga seperti core drill, seperti mesin tester lainnya. Lalu yang kedua non-destructive tester, kita menyediakan alat uji tidak merusak seperti uji dengan ultrasonik, eddy current dan lainnya. Lalu monitoring ketiga adalah monitoring sistem untuk berbagai aplikasi dari Principal, dan surveying equipment, alat untuk survei, baik survei udara, survei laut, bawah laut. Kedua adalah yang layanan kita adalah sensor dan monitoring dan kontrol sistem, dari mulai sensor-sensor yang akurasi tinggi, data loggernya, data akuisinya, softwarenya, kita bisa supply yang standar maupun yang custom. Karena kami juga punya engineer instrumentasi yang membangun software yang customized untuk aplikasi pemantauan dan kendali atau kontrol. Ketiga adalah kita menyediakan software CAE engineering. Itu kita perwakilan dari FEMtools untuk Finite Element Model Updating. Yang keempat, layanan kita adalah services. Itu pertama repair upgrade alat tester Anda, alat uji, instrumentasi, training, masuk training untuk fundamental knowledge untuk penggunaan dan analisisnya. Lalu juga services termasuk. Services kita adalah 3 grup. Services ini adalah testing, jasa pengujian, jasa ukur. Dalamnya ada jasa untuk 3D laser scanner. Ini sangat penting untuk misalnya membuat S-build drawing di antara aplikasinya. Struktur Anda yang tidak punya S-build drawing bisa kita buatkan dengan jasa 3D laser scanner ini. Non-destructive tester, kita mengevaluasi struktur dengan membaca dengan memakai ultrasonik untuk mengetahui mutu beton atau hammer test dan lain sebagainya untuk membantu di lapangan pengujian. Destructive tester, kita juga menerima jasa pengujian destruktif. Lalu ada loading test, statik dan dinamik, serta jasa untuk monitoring juga. Service kedua adalah engineering untuk analisis dan desain. Kita menerima desain jembatan, bangunan gedung, dan juga untuk evaluasi struktur. Yang ketiga adalah training. Okay. Manpower kita ada 3 grup engineer, yaitu civil engineering, instrumentasi, dan mechanical engineering. Pengalaman kami terkait di civil engineering ini, di monitoring, banyak sekali proyek terkait dengan yang ditangani di bawah direktorat jembatan, seperti jembatan-jembatan khusus, dan juga beberapa struktur lain seperti bendungan dan jembatan-jembatan yang dikelola oleh swasta. Ini adalah beberapa partner kami. Kami juga sering mensupport Komisi Keselamatan Jembatan dan Terowongan Jalan dan juga menginisiasi asosiasi HIMAMSI, Himpunan Masyarakat Monitoring Kesehatan Struktur Indonesia. Webinar kita membahas tentang monitoring dan evaluasi bangunan jembatan dan bangunan gedung dengan model updating. Kita perlu garis bawahi model updating. Model updating adalah model finite element yang diupdated, dikalibrasi, dan atau diverifikasi dengan data uji. Makanya ada istilah testing and simulation work together atau digital twin. Apa itu? Digital twin adalah representasi digital dari sebuah struktur dalam bentuk model finite element yang telah dikalibrasi dengan data uji. Jadi ada struktur, dibuat dulu model finite elementnya, lalu diambil data respon-responnya dengan testing. Nah, jadi ada simulation dan testing, lalu diupdated atau dikalibrasi atau divalidasi. Sehingga hasilnya adalah disebut digital twin. Itu kembar digital dari suatu model, dari suatu struktur di dalam komputer kita. Nah, model updating ini dibantu oleh FEMtools sebagai perantaranya yang berperan penting untuk melakukan model updating itu dengan otomatis. Oke. FEMtool berguna untuk bisa diaplikasikan untuk ketika pengujian periodik. Nah, ini adalah flow-nya. Jadi ada satu model finite element yang dibuat, lalu FEMtool berperan di sini untuk menggait testing engineer di mana penempatan sensor secara optimum. Dan setelah data pengujian diambil, direkam, lalu nanti dimasukkan ke FEMtoool lagi, lalu FEMtoool berperan lagi untuk melakukan updating model yang dibuat di awal. Nah, seperti kita ketahui, metode dalam analisa pengujian itu ada dua, yaitu vibration based atau model analisis, serta static loading test. Nah, vibration based atau model analisis itu adalah kita menggetarkan atau membaca respon struktur itu dari getaran. Jadi kita menggunakan sensor akselerometer terutama yang kita membaca perubahan-perubahan parameter fisik struktur itu seperti massa, kekakuan, dan damping. Itu bisa juga dipilih apakah metode eksperimental, artinya kita menggetarkan si struktur itu dengan penggetar atau dengan hammer. Nah, yang lebih akurat ya tentunya ya. Kalau dulu kita masih menggunakan truk, dan Tesido juga menyediakan nih alat-alat eksperimental ini seperti di gambar ini. Atau kita hanya membaca outputnya atau respon strukturnya saja dari sensor-sensor yang dipasang, sementara struktur itu tetap dioperasikan. Nah, bedanya adalah yang pertama tadi kita harus menutup akses operasinya, jalan ditutup, nggak ada yang boleh lewat, lalu kita naikkan alat penggetar ke struktur, lalu kita getarkan dan baca responnya. Yang kedua, yang operasional ini kita tidak perlu menutup jalan, tidak menutup akses, tetap digunakan, lalu kita membaca respon-respon dari struktur itu dari sensor-sensor yang kita pasang. Jadi beroperasi sambil kita mengevaluasi struktur tadi. Nah, metode yang pertama tadi adalah metode model analisis, yang kedua adalah metode static analysis. Nah, ini adalah metode di mana si struktur dibebani, lalu kita beban yang terukur tentunya dengan beban yang bertahap. Misalnya kita kita bikin modelnya, kita evaluasi beban maksimalnya, lalu kita pilih beban maksimal 75%. Jadi struktur kita bebani dari mulai 10%, naik 10% lagi, naik 10% lagi, 10% lagi, atau naik terakhir 15% misalnya. Ketika kita membebani itu, kita lihat perubahan-perubahan dari perilaku struktur. Kita menggunakan sensor-sensor diantaranya seperti GPS, atau robotic total station, strain gauge, atau laser scanner. Nah, dan sensor-sensor ini semuanya dibaca dan dihubungkan dengan beban. Dan kita di Tesindo menyediakan semua equipment juga untuk Anda jika Anda memerlukan. FEMtool difungsikan juga untuk permanen monitoring atau continuous structural health monitoring dan damage identification. Artinya di sini FEMtool diinstal di server yang sama dengan server penempatan data sensor. Termasuk di dalamnya juga server itu diinstal software Finite Element, di mana model yang dibuat di awal akan selalu diupdated secara otomatis ketika data dari ukur itu masuk ke server itu melalui perantaran FEMtool. Sehingga outputnya kita sebagai user, sebagai owner bisa mengidentifikasi rusak, di mana posisi rusaknya, berapa besar rusaknya, lalu bisa memperkirakan sisa umur struktur, tentunya dengan statistik data yang banyak ya, tentunya butuh data yang banyak. Nah, apa manfaatnya FEMtool itu? FEMtool itu complete system. Jika kita udah memiliki FEMtool, artinya kita tidak perlu lagi melirik yang lain. Seperti model parameter ekstraktor software juga di luar ada. Jika kita ada punya FEMtool, dia udah termasuk modul-modulnya, modul signal processing, model parameter ekstraktor, rigid body properties ekstraktor, termasuk di dalamnya. Dan FEMtool bisa melakukan updating model menggunakan beberapa jenis sensor sekaligus. Misalnya udah ada terpasang accelerometer, altimeter, anemometer, GPS. Kita bisa mengupdate secara terus-menerus dan sekaligus dengan FEMtool. Nah, ini bentuk interface-nya FEMtool. Jadi biasanya updating model ini bisa dilakukan juga dengan secara ini ya, trial error ya atau literasi. Nah, FEMtool ini membuatnya jadi otomatis. FEMtool juga bisa dioperasikan dengan Windows dan Linux. Nah, ini adalah modulnya, ada modul framework, dynamic correlation, model updating, optimization atau FEMtool full version. Dan ya ini selanjutnya ini presentasi saya untuk penjelasan singkat mengenai digital twin, test and simulation work together dan company profile buat Tesindo. Selanjutnya saya serahkan presentasi selanjutnya kepada Bapak Lukman Murdiansa, STMT terkait dengan evaluasi dan monitoring struktur jembatan dan struktur bangunan gedung dengan model updating.
Assalamualaikum warahmatullahi wabarakatuh. Selamat sore semua.
Assalamualaikum warahmatullahi wabarakatuh.
Pada kesempatan ini saya mau mempresentasikan tentang urgensi dari model updating. Next. Baik, kalau kita lihat definisi dari model updating, kalau kita mengacu ke SE Dirjen Bina Marga Bapak Ibu yang nomor 4 tahun 2020, yang sekarang itu baru disahkan ya tentang model updating. Yang model updating itu didefinisikan sebagai kalibrasi model finite element awal berdasarkan hasil uji ketat dan uji pembebanan statis gitu. Jadi intinya adalah bagaimana caranya menyesuaikan model finite element kita dengan model real yang ada di lapangan gitu. Nah, tujuannya adalah memang untuk nanti mendapatkan properti-properti struktur seperti modulus elastisitas, inersia dan sebagainya kayak gitu. Next, Pak Fikri. Nah, sekarang kita tinjau dari urgensi model updating. Kalau kita tinjau dari urgensinya, ya ada dua hal yang membuat model updating ini sekarang menjadi urgent kayak gitu ya. Perlu kita perhatikan, yang pertama itu adalah dari segi aspek legalnya, dan yang kedua itu adalah aspek teknisnya. Next. Nah, ini kalau kita berbicara masalah aspek legal, bulan kemarin ya kalau nggak salah ini SE ini surat edaran sudah dikeluarkan, yaitu tentang panduan teknis evaluasi struktur jembatan untuk dispensasi pengguna jalan yang memerlukan perlakuan khusus. Nah, SE ini dibuat untuk mendapatkan izin bagi pemohon izin yang menggunakan jembatan dengan beban itu beban overdimension overloading kayak gitu. Kalau kita perhatikan kalau di SNI kita beban jembatannya hanya 50 ton gitu ya maksimal kalau beban truk. Tetapi kalau truk dengan overdimension dan overloading melewatinya tentu beban kita bisa menjadi overload dan akan membahayakan struktur kita. Nah, jadi di sini di panduan ini, next Pak Fikri. Nah, di panduan ini juga terdapat bagaimana prosedur bagi para pemohon dispensasi untuk mendapatkan dispensasi, sehingga kendaraan itu bisa lewat di satu jembatan yang ingin dilalui gitu. Nah, yang menarik itu adalah diagram alir prosedur mendapatkan izin itu terdapat satu poin ya, yaitu kalibrasi model atau model updating. Kalau kita lihat di slide yang sebelah kanan ya, di sebelah kanan kita di situ terdapat kalibrasi model struktur. Nah, kalibrasi model struktur ini dilakukan oleh pemohon dispensasi kalau ada data-data yang tidak lengkap gitu. Data-data tidak lengkap, sehingga pemohon dispensasi harus melakukan kalibrasi model terhadap jembatan existing yang akan dia lalui kayak itu. Setelah dengan inspeksi-inspeksi khusus, inspeksi awal dan sebagainya kayak gitu. Nah, jadi ini adalah menjadi urgensi dari model updating dari segi legal aspek. Next, Pak Fikri. Nah, yang kedua, urgensi model updating dari segi aspek teknis, yaitu penilaian kondisi struktur secara global. Nah, kalau kita perhatikan di dalam panduan ya, panduan PLT 05/2002B, itu pedoman penilaian kondisi jembatan untuk bangunan atas dengan cara uji getar. Kita dapat melihat di panduan tersebut yaitu mengukur kesehatan atau kerusakan nilai kerusakan struktur, itu berdasarkan frekuensi kayak gitu. Jadi kalau kita lihat di sini di slide ini ada nilai kondisi ya, nilai kondisi struktur berdasarkan nilai frekuensi. Kita bandingkan antara frekuensi teoretis, yaitu frekuensi yang diperoleh dari FEM, dan juga frekuensi aktual. Frekuensi aktual itu frekuensi yang diukur dari eksperimental di lapangan seperti yang dijelaskan oleh Pak Fikri tadi. Nah, dengan membandingkan sehingga diperoleh perbedaan frekuensinya gitu. Jadi persentase perbedaan frekuensi struktur permodelan dengan yang ada di lapangan. Jadi kalau perbedaannya itu mencapai 18% sampai 20% seperti kita lihat itu ya berarti sudah dikategorikan sebagai buruk ya kondisi strukturnya. Tetapi yang menjadi pertanyaan kita adalah ketika kita memodelkan F teoretis kita ini, kita memodelkan struktur, kemudian kita run analisis dengan modal analisis untuk mendapatkan frekuensi. Nah, jadi pertanyaannya itu adalah apakah benar-benar permodelan dari FEM kita itu sudah mewakili itu, mewakili kondisi yang ada di lapangan, struktur existingnya, sekalipun struktur itu baru. Karena pada prinsipnya mungkin saat pengerjaan konstruksi mungkin ada kekurangan-kekurangan atau sebagainya, sehingga perencanaan awal seperti nilai modularitas mungkin yang tidak tercapai atau berlebih juga bisa, atau mungkin terjadi cacat konstruksi gitu, bisa-bisa aja gitu. Sehingga kalau kita bandingkan dengan nilai teoretis dengan nilai aktual nantinya, ya tentu ini tidak akan memberikan hasil yang tidak mungkin kurang tepat kayak gitu. Nah, sehingga perlu kita lakukan model updating ini. Next, Pak Fikri. Nah, yang kedua adalah untuk penilaian kondisi nilai kondisi dari komponen suatu struktur jembatan misalnya kayak itu. Ini studi yang saya lakukan dengan Pak Robi. Ini jembatan di Jogja ya, jembatan Rekso Diningrat. Kita melakukan evaluasi kinerja struktur jembatan terhadap beban gempa terbaru, gempa 2016 ya, SND 2833. Nah, kami melakukannya dengan memang ini tanpa model updating ya, tanpa model updating karena kita keterbatasan biaya juga, kita tidak bisa melakukan eksperimental. Nah, pengujian seperti ini mungkin sering dilakukan gitu, sering dilakukan untuk mengevaluasi sebuah struktur. Lagi-lagi sebetulnya ya balik lagi ke pertanyaan awal, apakah permodelan FEM kita ini bisa mewakili ya kondisi struktur real yang ada di lapangan sebetulnya, sehingga hasilnya juga sebetulnya kalau tanpa ada kalibrasi model atau model updating ya boleh dikatakan bisa kita pertanyakan kayak itu ya. Nah, kayak ini. Nah, dari sini kita mengevaluasi kekuatan pilar Bapak Ibu ya, kekuatan pilar, kemudian compression arch seperti yang terlihat di ini. Nah, di sini kami coba melakukan dengan modal analisis ini model push over analysis. Kita nge-push dengan beban SNI terbaru kayak gitu. Nah, dari sini kita peroleh kapasitas pilar itu hampir mencapai puncaknya gitu dengan beban SNI gempa terbaru. Tapi ini dengan catatan tanpa model updating. Karena ketika kami survei ke sana juga sudah ada terjadi ya retak-retak kecil kayak itu di jembatan, sehingga pemodelan FEM-nya tidak mewakili kondisi real yang ada di lapangan kayak itu. Kalau kita tinjau dari prosedur umum FEM ini, kalibrasi model, ini secara umum saja. Yang pertama itu adalah pemodelan finite element FEM-nya. Dan yang kedua itu adalah pengujian lapangan. Seperti yang sudah dijelaskan oleh Pak Fikri tadi ya, pengujian di lapangan ada dua. Yang pertama itu adalah ambient force, vibration test. Yang kedua itu adalah force vibration test. Kalau kita ambayan, seperti yang sudah disampaikan Pak Fikri tadi, ambayan adalah kita mengukur respons struktur berdasarkan beban operasionalnya gitu. Jadi kalau di jembatan ya kita cuma masuk sensor tanpa menutup lalu lintas kayak gitu. Jadi bebannya hanya beban yang lewat atau beban operasional. Kalau force vibration tentu yang seperti yang sering dilakukan ya di jembatan seperti bumping test dan seperti ya uji getar dan sebagainya kayak gitu. Nah ini memiliki kendala itu kita jalan. Kalau biasanya dalam model updating dari beberapa referensi yang kami baca yang banyak digunakan itu adalah ambient vibration test. Kemudian data dari finite element FEM, data dari pengujian lapangan ini nanti itu akan diolah sehingga diperoleh struktur yang sudah terupdate gitu permodelannya. Next, Pak Pipi. Nah, ini contoh penerapan model updating. Ini ambil dari papernya Chen et al. Ini melakukan model updating di jembatan New Market Viaduct. Ini di New Zealand. Ini menggunakan FEMtools ya. FEMtools. Nah, jembatan ini dengan panjang 660 meter, terdiri dari 12 bentang. Itu single cell box girder ya. Tetapi itu di atasnya struktur atas ada single cell box girder yang berdekatan. Dan lebarnya itu lebih kurang 30 meter. Next, Pak Fikri. Nah, pada jembatan ini dalam pengujiannya itu menggunakan ambient vibration test, di mana di dalam gelagarnya itu dipasang sensor-sensor seperti yang terlihat di sini. Nah, pada jembatan ini juga diambil data-data getaran itu di sepanjang jembatan tadi itu dengan spasi pemasangan sensor itu 1/8 dari panjang bentangnya gitu. Jadi setiap 1/8 dari panjang bentang jembatan itu dipasang sensor, kemudian diukur gitu, diukur getaran-getarannya. Nah, di sini dipasang dua sensor, sensor kiri dan kanan box yang bertujuan untuk mendeteksi seandainya terjadi torsi kayak itu, sehingga perlu dipasang dua sensor akselerasi kiri dan kanan di dalam boxnya. Yang ini bertujuan untuk pembacaan seandainya jika terjadi torsi kayak itu ya, nanti torsinya bisa terbaca. Next. Pak Fikri. Halo, Pak Fikri. Next. Nah, di sini dari di slide ini kita bisa melihat ini adalah contoh bacaan dari sensor, yaitu acceleration time series-nya. Di sini terlihat data-data percepatan yang diukur, itu arah transversal dan arah vertikal ya, arah transversal dan arah vertikal. Itu yang warna kuning getaran arah transversal, kemudian yang warna biru getaran pada arah vertikal. Nah, dengan metode OMA tadi yang sudah dijelaskan oleh Pak Fikri, Operational Model Analysis, yaitu dengan EFDD, pada studi ini dilakukan dua metode untuk mendapatkan frekuensi struktur jembatan, yaitu dengan EFDD dan juga SSI, kayak itu. Sehingga diperoleh frekuensi natural jembatan seperti yang kita lihat di gambar 6 itu. Di gambar 6 dan juga di tabel 1. Data-data frekuensi yang diperoleh dari pengujian ini nantinya akan dijadikan sebagai bahan acuan dalam melakukan model updating nantinya untuk model updating struktur jembatannya. Next, Pak Fikri. Nah, di sini adalah mod shape dari uji getar yang diperoleh dari pengujian lapangan tadi ya, dari ambient vibration test. Di sini ada mod 1, mod 2, mod 3 dan seterusnya kayak itu. Nah, di situ mod 1 itu adalah T itu mewakili transversal ya, kalau V vertikal. Next, Pak Fikri. Ini adalah pemodelan struktur jembatan New Market tadi, yang terdiri dari 12 bentang kayak itu ya. Pemodelan dilakukan dengan software SAP 2000. Nah, di sini kalau kita perhatikan dari permodelan SAP itu di tabel 1, di tabel 2. Di tabel 2 itu kita bisa melihat perbedaannya ya. Perbedaan AVT itu adalah frekuensi yang diperoleh dari pengujian di lapangan. Kemudian yang FEMtools itu adalah frekuensi awal yang kita peroleh dari analisis struktur dengan SAP yang belum diupdate ya. Nah, jadi yang frekuensi struktur yang kita peroleh dari SAP itu menjadi bahan dasar untuk diolah. Jadi dari tabel 2 itu kita bisa melihat misal di frekuensi di mode 1 itu untuk AVT itu 1,05 Hz ya. Kemudian dari FEMtools yang diperoleh dari SAP itu 0,93. Nah, dan seterusnya ke bawah kita bisa melihat ada perbedaan-perbedaan frekuensi yang diperoleh dari pengujian lapangan dan dari SAP gitu. Nah, sehingga dari sini nampak oleh kita urgensi ya kenapa model updating itu perlu dilakukan. Nah, di tabel 3 itu adalah perbandingan frekuensi natural struktur ketika sudah dilakukan update model. Jadi sudah diupdate modelnya, kita sudah bisa melihat dari AVT, kemudian dari model kita bisa melihat ya 1,05, 1,08 kayak itu perbedaannya ya kecil, sekitar 2,9% kayak itu yang terbesar ya di mode 1, di mode 2-nya perbedaan ya 2,2%. Dan seterusnya untuk di mode-mode selanjutnya. Nah, next Pak Fikri. Ini adalah perbandingan mode save antara pengujian dan mode save permodelan struktur setelah diupdate ya. Nah, di sini nampak kita lihat kalau yang berwarna merah itu adalah model yang sudah kita update. Kita bandingkan dengan permodelan yang ada di lapangan kayak itu. Next Pak Fikri. Nah, model updating, ketika melakukan model updating, intinya mungkin logikanya itu adalah sama dengan teknik curve fitting, lebih kurang kayak gitu. Nah, jadi variabel-variabel kita yang kita ubah agar model FEM dari struktur kita itu mengikuti kondisi real di lapangan, sehingga banyak parameter yang mesti kita rubah melalui dari proses model updating ini. Kalau di jembatan ini ada beberapa parameter yang dia rubah, sehingga tadi bisa kita lihat produk frekuensi natural itu hampir sama ya. Nah, yang pertama itu yang dia rubah itu adalah luas penampang, variabel yang dirubah dari proses model updating, kemudian momen inersia, kemudian modulus elastisitas, dan berat jenis kayak itu ya. Nah, kalau kita lihat di tabel 4, itu tabel 4 memperlihatkan parameter jembatan sebelum diupdate. Sebelum diupdate, itu kalau set 1 itu adalah data-data gelagar ya, data-data gelagar, ada sampai 6 itu adalah data-data gelagar, ada luas penampangnya dan momen inersianya kayak itu, kemudian modulus elastisitasnya dan sebagainya kayak itu. Nah, di tabel 5, kalau kita perhatikan itu ada parameter bridge setelah diupdate. Setelah diupdate, nah kalau kita perhatikan terjadi perubahan ya, yaitu 22,7 menjadi 23,14 gitu. Dan parameter-parameter yang lain juga terjadi perubahan. Yang paling berpengaruh itu kayak di modulus elastisitas ya, dari 36 GPa menjadi 39 gigapascal kayak itu. Nah, begitupun yang untuk elemen-elemen data pilar dan juga data bearing kayak itu ya, di set 9 sampai set 11 itu adalah data bearingnya. Nah, dari sini kita perhatikan bahwasanya dengan melakukan model updating, kita bisa melihat banyak parameter yang mesti kita rubah. Konstruktur yang boleh dikatakan menyerupai atau mewakili kondisi real yang ada di lapangannya. Dah, mungkin itu saja dari saya, Pak Fikri, untuk presentasi siang ini.
Can you see the screen?
Yes, can.
Okay. So I can start now.
Okay,
Right.
please.
So good afternoon. So I will follow up on this presentation by Lukman with some additional information about the FEMtools software, and also show you how we have applied it for projects like bridge monitoring and building simulation. So first, about the company. So we are a software company specializing in structural dynamics simulation, and we are specialized mainly in the validation and updating of finite element models. And the unique feature of the software that we develop is the possibility to combine simulation and test data in one single software. So FEMtools is therefore multifunctional, cross-platform, and can work with different FE solvers. And as it is based on a framework that can communicate with different FE software or have access to various types of test data, it can also be used to develop custom solutions using the integrated scripting language. So can be for simulation, model testing, test planning, correlation between FE test, updating, design optimization, and so on. So it's not for one single purpose, it's multi-purpose. It has a number of standard features, like for simulation, test planning, correlation, and updating, but it can be extended with additional tools depending on the environment. So it can be considered as an integration tool of combining test data, FE data from different sources, tools like MATLAB, Excel, and other utilities that may be available, and they can all be integrated in the software. Data can be exploited, and for reporting you can use the built-in reporting tools or make custom reporting tools. The process can be automated, or the software can be integrated in some vertical tools like development of digital twins, structural health monitoring, and material identification, for example. Model validation and updating is becoming increasingly important to reduce uncertainty on the simulation model assumptions. So in order to make better use or make increased use of simulation models for decision making or for monitoring applications, for example, it is important to have high confidence in the results produced by simulation model. And therefore, there is now work being done to include the validation activity into the standards, like the standards proposed by American Society of Mechanical Engineers, ASME, or the International Standardization Organization, ISO 9000, to specify that validation is required for the quality control of simulation models. And it has been agreed that for this purpose, reference data must be used that is real-world data. So it must be the results from physical testing of structure. And so also it's important to consider that a simulation model is serving a specific goal. And so there can be different models for the same structure depending on the application. And so it is important to consider the intended use of the model when doing a validation, because a model can be valid for static analysis, but it cannot be valid for dynamic analysis, for example, or vice versa, because the complexities of the model can be different depending on the application. And so the intended use will dictate the choice of parameters and responses. So responses can be modal, static, operational, strain, and so on. Parameters can be related to stiffness, mass, damping force, again, depending on the application. Also, the parameters can be local, parameters for some area of the structure or for a joint, for example, joint stiffness, but can also be global parameters like material properties that apply to the structure, entire structure. So this activity of validating and updating is more the technical description of what it is, or the mathematical part, but in fact it can be used as a tool for increasing the quality of a model, but can also be part of a larger vertical application like structural health monitoring, where model updating is just one component of a larger system, whereas for design purposes, the validation and updating can be used to increase the quality of the model for better predicting the response of an optimized structure. So when it comes to assessment of civil structures, I saw that Lukman already did some introduction on this, so I will be very brief, but it's clear that that this is a growing application area thanks to the use of operational model analysis, which has become a powerful technique to identify the vibration properties, and that can run without interruption of a structure. So you can keep a bridge, for example, in operation while doing the testing, which is very important for permanent monitoring of a structure. So the goal of using simulation models and updating reference simulation models can be to identify structural damage, which can be caused by corrosion, fatigue, foundation settlements, impacts, earthquakes, typhoons, overload, or chemicals. So this is just the different types of damage that can be causing the change of the vibrational structure. And it's important to identify these possible causes, because in the simulation model, it is necessary that if you are monitoring the vibration of a structure, that the simulation model is capable of representing the damage that may occur to the structure. So the sensitivity of the simulation model to changes in stiffness, mass, or damping that are caused by these different types of structural damage should exist, because if the structure model, and you can see here on the right hand side simulation model of a tower building, is a very coarse simulation model, and of course it is not going to be sensitive for a damage of a small part of the structure. So this is more to monitor the global and very important changes to the structure. For example, the impact of an earthquake, for example, which is in fact the reason for this model is earthquake simulation. Is okay to do that with a coarse model, because it will have an overall impact on the structure. And if there is damage caused by earthquake, it's probably going to be detectable through a coarse model like this. But it will not be possible to detect damage in one steel member or in some part of the structure. So you have to adapt the simulation model also to the type of damage that you are trying to detect. The need for this type of technology is very important. For example, here it is estimated that 27, or let's say almost 30% of bridges in the USA are structurally deficient and will need to be repaired or replaced or retrofitted. So this is a huge problem for the future in order to be able to test and classify this large amount of infrastructure, which is important for the economy, for the country. And this is only in the USA. The same is true for European countries, and I assume also for Asian countries. So it is potentially a very expensive, going to be very expensive to do this kind of repair. So it's important to find techniques to quickly assess the condition of bridges. This can be with temporary installations. For very large, important infrastructure, it can be a permanent installation. Also considering the risk that is involved. And for example, in Italy, there was last year a sudden collapse of a bridge that was very important for the traffic inside the city. So this kind of accidents should be avoided and can be avoided by permanent monitoring of the bridge, so that it can be stopped operating or maintained in a better way to avoid this kind of accidents that has impact on, well, people's life and also the economy. So simulation using finite element analysis is very powerful, but of course it's not perfect. There are modeling assumptions. There is limitations to the fidelity that can be afforded, the size, the technical challenge of simulating a complex structure. And so it is necessary to adapt the model to the purpose, as I already mentioned, but also to validate that the chosen simulation model is fit for the purpose, and if necessary, use updating technology to improve the model to serve its specific purpose. So this validation and updating can be done by comparison with test, of course, can be done with comparison with other models, more refined models, reference models. Updating can be done using trial and error, but of course it's much more efficient to do this in an automated way. So, and the benefits is that it is part of a learning curve to learn how to develop models for specific purpose, how to estimate the input parameters, and so in brief, gain expertise for future modeling. The process itself can be automated once the parameter and responses have been selected. So this is the engineer's responsibility to make a choice about all the parameters that are potentially selectable. Again, it's depending on the application. Is it a local change, global change? Is it for improving the validity of the model for design optimization? And is it for damage detection? So the application will decide the parameter choice, but also information about uncertainty, information about the correlation analysis that was done to observe how is the difference between simulation and test. So what could be the parameter that can remove this difference. Also, sensitivity analysis is used to check whether the parameters that are selected can change the responses. So it is important to adapt the choice of parameters to the responses that need to be modified. So once this is done, then the automated loop can start, which includes the parameter estimation. So it's a type of optimization, specific type of structural optimization. to reduce the difference between the test responses and the simulation responses. And so from this is a equation solving leading to a new parameter value that needs to be implemented in the database. And so with new parameter values for materials, for plate thickness, beam stiffness, and so on, the finite element model is updated and needs to be solved again. So this can be with internal solver that is included in FEMtools, or the external solver that is used for the simulation. When the new results come back, the correlation analysis is repeated to see if there is improvement or if there is enough improvement to stop the process. If not, this has to be repeated. Typically, it will be between 5 to 10 iterations in order to improve the simulation model sufficiently. It's not the goal to have zero difference between simulation and test. This is not necessary because there is always some uncertainty on the test data. There is also some variability on the test data or some noise. So it's only necessary to get closer to the test data in such a way that on average the simulation model is like 1, 2, 3, 4, 5%. It depends on the application, but it's certainly not the ambition to go lower than 1% correlation or the difference between simulation and test if the uncertainty on the test data is also 1%. So how close simulation should be to test depends on the uncertainty in the test data. So therefore, model updating typically will require less iterations than optimization. So 5 to 10 for updating, typically 50 to 100 for optimization. The choice of responses depends on the application type, of course, like the parameters. Here you can see different possibilities, whether it's mass responses, static responses, modal responses, frequencies, mode shape, frequency response functions as responses, or deflection shape, operational deflection shape responses. So they can be done separately, or they can be done as part of a sequence, ideally for a complete validation of a model, validation of mass, stiffness, damping, and force. So 4 groups of parameters. You cannot do this only with static analysis, for example. With static analysis, you can only update stiffness. So if you also need to validate and update mass and damping, you will have to use dynamic responses. Model-based is most popular approach because the test data is relatively easy and fast to obtain using a modern technology like accelerometers, using operational model analysis. So it is relatively easy to obtain good quality reference data like frequencies and mode shapes, which can be compared to the result of simulation. And so in a correlation analysis, from their sensitivity analysis, and from their updating. It's also good practice to use the baseline finite element model to do a design of the test setup. So we call that pre-test analysis, which is about the optimal choice of the sensor locations. If it's for mechanical industry, there's also a choice how to excite a structure with hammer or shaker, how to suspend the structure if it's lightweight structure. So this is less important for civil structures where, of course, the excitation and the suspension is already imposed, but still in general speaking, test planning is very important to make sure that the test conditions are optimal for the process of modal analysis. So there can be different types of testing, of course. Also, so apart of modal analysis, there's operational deflection testing. So operational testing, you can use transfer functions. You can use rigid body property extraction to extract mass, center of gravity, and use those as references. Or you can use static testing, use displacement, like GPS receivers, or strain gauges, or optical fibers, or full field testing, lasers, and digital image correlation. So applications, I think this is clear. So it is to improve the simulation model for further simulation, but you can, depending on the choice of parameters and responses, it can be for specific identification of properties like material or damping, to build coarse models for faster simulation, so simplified models, but using a high fidelity reference model as a reference. Exploratory model updating is a kind of researching for areas where mesh refinement may be needed, or for also part of damage detection, so detect which part of the structure may need to be modified. So in terms of simulation model, it means that the modification means like simulating the damage. If there is a crack in the structure, it's like a reduction of stiffness. So it means your FE model will be modified so that in the area of the damage, the stiffness is going to be reduced to simulate the physical damage. So if you do not know where this damage is occurred, then you can use what we call exploratory model updating, where you can use a lot of parameters. It's an element by element. Element in the simulation model will become a parameter. So this allows for local damage detection or damage localization. So leave it there. So an example of mesh coarsening. So here you can see a reference model is used in car industry, using solid elements, using stiffener ribs, and so on. But this model is relatively expensive when you have to do massive simulation, like for acoustic purposes, for example. Then here a simplified model is created. Is much simpler, uses only plates, no stiffener ribs, but it can produce the same frequencies and mode shapes. For acoustic simulation, the two models are equivalent. So this coarse model is then to be preferred because it's much faster to do massive reanalysis compared to the refined model. So this is very common practice in mechanical industry, but also in civil engineering, it can be used to create like condensed models for faster analysis compared to very detailed model of a structure, which can become really big models if you want to do a high fidelity model of a bridge or a building that can become not manageable for quick reanalysis. So then you need simplified or condensed models. This is an example of exploratory model updating using a model of a car engine. You can see the result of element by element updating shows us that there is some areas, you color it in green, red, and orange, that indicate areas that need attention. The blue areas are okay, so this is close to zero change. So, but some specific locations are modified or need modification in order to have a nice correlation between the first 10 mode shape of this engine. And so this is now showing the most likely areas that need improvement. What the improvement is depends. I don't think this will be a matter of damage, but it can also be the need for mesh refinement or improving the detail of the geometric meshing in those areas. And another example here of exploratory model updating, where you can see for this part of a hard disk, green in this case means 0 changes are needed, but there are some areas like this central part or this corner part that needs modification in order to have the convergence that is shown here with an average error on the frequency from 15% to down to 1%, and have a very nice correlation. So if you do not know what change is needed, then exploratory model updating element by element is like error localization or damage localization in a structure, because using a software like FEMtools that can support element by element updating using thousands or 10,000 parameters is no problem, then you can create this kind of graphic visualization of the areas that need a change in stiffness or mass. Another example is extreme condensation of the model. You can see here the model of an aircraft, where the simulation model is only the blue lines or the black line with the blue markers. So it means that a component like a fuselage or even a wing is represented by a beam. And so it is really very challenging to find the equivalent beam properties for like the wing or the fuselage. And so if you have results from vibration testing, then it's possible to use that as a reference to do this estimation of the beam stiffness. And this kind of model is very important for air elasticity analysis or flutter analysis. And so model validation is quite essential. So software like FEMtools is being used for many years in industries like aircraft. So companies like Boeing or Airbus, they are using this for this application. And I think it's also important for civil engineering structures like bridges, because the need for simplification of the model, it will be not always possible to model every component, every beam in the structure. And so by using more global simplified models that are still useful for not for all applications but for many applications, the more of the simplification is done, the more there is a need for a validation of the equivalent model. So this is clearly illustrated by this type of application for aircraft modeling. Also important in structural dynamic simulation is the estimation of damping, which can be done by using frequency response data. So you can, instead of using mode shapes, which are derived from the free FRFs, you can use the FRFs itself, the raw data, to check the matching of peaks, resonance peaks, but also adjust the damping in the simulation model in order to match the amplitudes at the resonance peaks. So when a simulation model is used in a monitoring system, we will often call it a digital twin, which we define as a simulation model that represents the true physical product to a sufficient extent and considering its purpose during the entire service life of the product. And so this is quite important. So during the entire service life, because it means that if like for a bridge, the lifetime is 100 years, it means that during this entire period, if the simulation model is going to be used for monitoring and for damage detection of the bridge, it has to remain up to date for the entire service life. So if any changes are made to a bridge, like retrofitting or reinforcements, or even if damage has occurred, that should be introduced in the simulation model to keep it up to date. And so that means that model updating then becomes a permanent and a continuous part of the system. So it's not a one-time operation at the beginning, but especially for structures with a very long service life, it will be important to repeat certainly the validation, the correlation permanently, and also prepare for continuous updating of the structure if the structure changes. So using these simulation models as digital twins can be used for different applications, like using the model as a virtual sensor. So the finite element model becomes like a virtual sensor that is capable of computing the strains, the stresses in the structure, as competing with the instrumentation, like strain gauges, where a strain gauge will measure on a number of pre-selected locations with a limited number of channels. The finite element model can find or can simulate the strain and stresses at any location. So that is clear advantage. So it is also a cheaper solution to maintain, and it also produces much more results than the physical instrumentation. Of course, as I said before, this requires that the model is kept up to date. Another application is force estimation. So from the observation of the deformation of the structure, it is possible to estimate what are the forces. So if the monitoring reveals changes between the test data and the reference simulation data, then this information can be used to localize and quantify damage. So using techniques like exploratory model updating, as I shown on previous slides. So again, it is necessary to make the model a true representation during service life, and also to adapt the simulation model to the unique structure. So it is really a digital twin in the sense that it's a unique model for a specific structure. Of course, depending on the application, like damage localization, it's important to use high fidelity models and very high quality test apparatus for good quality test data. So the damage identification can be done at 4 levels. First of all, just detect the presence of damage. This can be done by just comparing frequencies. A shift in frequency indicates something has happened to the structure. Then location of damage will require more data, like the mode shapes, so that there is local information available. The severity of the damage will require that you have also quantified the amount of change in terms of stiffness change, for example, telling you whether it is becoming dangerous, if it's so the quantity of the modification of the structure, and then from there you can also do stress analysis and do fatigue analysis to predict the remaining service life. From an updated finite element model that has included the damage, so it represents the actual structure, the actual damage structure, and so this allows you to also update the prediction of service life compared to at the beginning of the operation of a bridge, for example. The service life can be determined to be 120 years. So it is possible by regular testing and keeping the bridge model up to date to update this estimation of residual service life depending on the true behavior of the bridge. So how many vibration cycles have been measured, because there is permanent instrumentation that can do that. So using rainflow counting, it's possible to count all the cycles, and then you can predict how far the structure has progressed in its surface life, and if it's faster than planned, then it may need inspection and repair. If it's slower than planned, then it means cost saving is possible, because the physical inspection can be slowed down, because there is obviously no damage to the structure, or it has been excited by less cycles than it was predicted. So the quantification of the damage will require that a reference model is available, ideally at the beginning of the service life of the bridge, when the structure is still undamaged. And then, so the updating can be done by using parameters that are representing the potential damage in the structure. So like local stiffness, for example. Okay, so FEMtools can also be used for the development of digital twins, because they must be custom developed. They are unique models, so require a unique finite element model. And so all the tools for scripting, interfaces, databases, solvers is all included in FEMtools to do that. So I will briefly show two cases where FEMtools was applied. So first is the Hong Kong Stonecutters Bridge, which is a suspension bridge of almost 1 kilometer long. And the towers, with 2 towers that are almost 300-meter high. The bridge opened in end of 2009, so it's like 10 years in operation. And FEMtools was part of the one of the monitoring tools in the control room for this bridge to well, the following purposes: to provide an automatic system that can show information about the bridge operation and maintenance, but in case of FEMtools, it was about the GPS receiver, so the deformation of the bridge, and the modal behavior, so using accelerometer to do operational model analysis. There are many more systems on the bridge, like strain gauge. I think here is a list of sensory systems. So There is 1,700 sensors installed on this bridge, including, well, the majority is strain gauges, but you can see many more sensors. So what was used in the project that included FEMtools was the accelerometers, but not all accelerometers are used. So only 8 accelerometers on the bridge deck and 1 on each tower. So 8 accelerometer, but also 8 GPS systems. So in general, this monitoring system will be used to create a database so that can be exploited for helping in the design and construction of new highway infrastructure. So as a learning, how to learn how the bridge behaves. So obtain information about real life behavior of the bridge, which is otherwise not available. And then also to plan maintenance and rehabilitation of old highway infrastructures. So it's also like a source of information that can serve as an example for other similar structures in the country. Of course, the structural health monitoring also is used to evaluate the structural safety and also to determine the priority for inspection and maintenance. This is a screenshot of the main monitoring panel that we developed. So here you can see a 3D view of the bridge simulation model. And the deformation that we are looking at is based on the GPS receivers on the bridge deck and the 2 towers. And so, because this is only at 8 locations, it is necessary to do some kind of expansion so that we can project this onto the bridge. Here you can see the GPS displacement coming in every second. And so we can show a real-time deformation of the bridge. The coloring that you see is the stress, von Mises stress. I will show this panel at the end of my presentation using the real screen. So here is an overview of the procedure for processing the data. So briefly, we have raw acceleration data that is read from an SQL database, which is the data is added to this database by the acquisition system. So this is a separate part. So the acquisition system is adding data, and we are just going to, every second, we are going to extract new data from this database. And so we do OMA, so operational mole analysis, with the internal tool in FEMtools, or using external tool. We have viewers, so for visual display of the results, or for analysis like correlation and model updating. Here you can see the principle of the expansion. So this is the test model with only 8 sensors. We can expand this into the FE model like this. Of course, here is a bit exaggerated amplitude, but you can see how we can go from the test data at a very low number of locations to estimation of the true bridge deformation visualized by the finite element model. And so from this deformation, we can then compute the stresses in the bridge. And this is done using the following procedure, where the acceleration data is used for operational mole analysis and providing a reference model data that is compared to the simulated. And here we can do correlation and updating if necessary of the bridge. When the model is considered valid, we will bring in the displacement time history, which is the GPS data, and we will use that deformation in order to estimate the deformation of the bridge deck on the towers, and do a stress recovery based on the FE model stresses. The FE model stresses are obtained from the updated FE model and is stored in a database. So it is possible to compute the stresses in a fraction of a second by just recombining the modal stresses. And so therefore we can show real time what the stresses are as the GPS data is coming in the database. You will see that in the demonstration at the end of my talk. We have here, you can see a report from a 24 hours monitoring of frequencies. You can see that frequencies are fairly stable. There can be some variation due to temperature, due to traffic, because cars and trucks on the bridge, they will add mass to the bridge and will then also change the frequencies. So all that has to be taken into account when doing damage identification. You also have to take into account the changes to the bridge caused by the traffic and by the temperature. The damping, on the other hand, is much more sensitive to condition of the bridge. Like, I mean, if there is a lot of cars on the bridge, for example, or they are driving, or they are standing still because of traffic jam, these are like masses that cause like tuned absorber on the bridge deck, and so the vibration amplitude can change, and so the damping is very variable depending on the hour of the day. Here's some additional plots from the monitoring panels, like stresses, moments in the tower. You have here some histogram. It's called the demand ratio of actual load in some section. And here is a fatigue life assessment. So the red curve is the maximum that is imposed by some standards, and here these dots are the actual consumed service life. So there is a very big margin, but this was done in the first year of the bridge operation. So obviously there is no problem at this moment. A second example is a 48-story building in Vancouver, which was tested by our friends in Vancouver University. So they were trying to capture the first 6 to 9 lateral and torsional modes of this bridge, of this building, sorry, and use this model for earthquake engineering applications. So here you see a section of the tower, the shape of the section, an accelerometer sensor, and here some typical response functions that you can obtain from this bridge, from this building. So with some clear peaks, and this can be used for operational mole analysis. So here you see the FEMtools model in blue, with in red the position of the sensors. It was possible to extract 6 modes. Here the reference frequency, and then the results before and after updating, the mode shape correlation. So there was mainly an issue with the 3rd and the 4th mode shape. The other was already well predicted before updating. And here some examples of changes. E is elastic modulus, H is thickness. But what was observed here is that the variation that is needed can sometimes be very, very big. And this is because the finite element model is really a very coarse representation of the true structure. And so because everything is using using beam elements, the properties are very much equivalent properties that are estimated. It's a bit similar to the aircraft beam model that models like a wing. I mean, what is the stiffness to be estimated for every location of that beam is really a matter of estimation of equivalent properties, and so it is considered not unusual to have large modifications that are needed, because these are not really true physical material properties, but they are more like equivalent properties. So the elastic modulus is more like a stiffness indicator rather than a material property. Okay, so to conclude, simulation model verification, validation, and updating must be part of every engineering process and digital twin development. The validation and updating itself is a process. It's not just like solving a system of equation. It's really like a process that is like almost like a medical examination with observation, diagnostics, doing specific testing, double testing, interpretation, in order to come to some conclusion about what is needed in terms of parameter selection, and then and also knowing what is the purpose of the simulation model. And when that is done, the process of changing the parameters can be automated, but there is a lot of effort needed before that in order to plan the test, do good quality testing, and to make the appropriate selection of the parameters. So the applications will determine the choice of parameter and response. And so a specialist CE software like FEMtools has been developed especially with this challenge in mind, to become like a general purpose tool that can provide all the utilities that are needed for this purpose. So all the interfaces, graphics, solvers, and so on. Also the API for custom development and automation, and the possibility to integrate this in an existing CAE workflow. Now, additional information can be found from our website or can be obtained from Testindo. Okay, so this is the FEMtools standard screen with the menu, the tables, graphics, and the console. And inside here we have a window that is the customized window developed for this project. It is a window that is similar to a web page window, so it's using HTML, but with additional JavaScript interface for the graphics. So this runs, this HTML window or web page runs inside the FEMtools environment. We have also customized the menu. As you can see here, we have added a specific menu for this project. So V8 is SHMS, stands for Wind and Structural Health Monitoring System, where we have access to the monitoring panels. So this is, in fact, what you're looking at now, the start of this, the main monitoring panel. But we also have access to special purpose commands like acceleration data reader to read data from the database, acceleration data from the database to do operational mole analysis, or import data from a file. We can then do mole analysis using external tool like Artemis, or using the built-in FEMtools MPE, model parameter extractor. So we have two ways to do a mole analysis. And then the last group of commands is to identify the list modal parameters, plotting, correlation, and graphics reporting. So this is the specific commands. After this, it is possible to use the standard tools like model updating or sensitivity analysis in FEMtools to do additional analysis. So this menu also opens the monitoring panel. So I already have it open here. And then so here you can see a number of panels available. So GPS, hourly variation, monitoring of displacement and stress, correlation monitoring. So these are the three classes. I have some demo data for the displacement monitoring. So I can open this panel. I can also make it a bit larger. You can also make it full screen. So here you can make it full screen. So now we have here at the bottom, we have GPS data coming in, and you can see that for this data we have maximum of about 200 millimeter deformation. So but the scaling is set up for 1200, so this is the maximum possible deformation in the bridge. So I can now start an animation loop that you can see is, this is now, of course, it's a demonstration. So we are using, we are looping over this short recording, 15 or 16 seconds of recording we are looping, but you can see that this corresponds to a swinging of the bridge. So it is possible to connect the system to the real-time monitoring, and so in that case this will be like one step per second, or 5 seconds. So this can be controlled. The monitor interval can be controlled in the settings. Now, it's also possible to import historical data. In that case, we will have something like this, where we loop over an amount of data that is read. That can be like 1 hour, but can also like much longer or much shorter recording of the data, which is stored in the database. So you can specify the start time and end time here in the box. So what we are looking at now is the test model, and the test model is just the deck and the 2 towers with 6 sensors here on the deck, and the 2 tower tops that are changing. The rest are not moving. So they are just to improve the visualization of the model. Now we can do the expansion to FE by clicking here. And so now we see the FE model, how it moves. You can see the bridge deck. And so this is obtained. It's a bit exaggerated, of course, for better visualization, but this is obtained from this model. So using only 8 GPS receivers, we can simulate what is the bridge deck deformation and the tower deformation. And we predict this deformation as a linear combination of the mode shapes of the bridge. So therefore, it's important to have the prediction of the mode shapes right. And we know that it's right because we have also done operational modal analysis testing and compare the mode shapes between the FE model and the test model. So from here, we can open other specific panels, like showing the tower positions with respect to the reference, or the bridge deck torsion. You can also here see the movement of the bridge deck vertically or horizontally. We can look at GPS data as it comes in at the different locations. So the west quarter, midspan, or east quarter, so marked by these red circles. Can also stop and just do a step-by-step if you want. So same for the tower top. Can have also the information displayed on the bridge deck, top view, front view, 3D view, perspective view, and then here tower east and west tower view. Can also look at the moments in the towers. East tower at the piers, or at certain section of the deck, bridge deck. So here already we can see stresses, the girders. So at different location in the longitudinal girders, cross girders, or at other locations called the troughs on the bridge deck. So here, I will stop it here. So here you can see that we have at least all these locations, we have estimation of the stresses in those locations. So can also obtain strains and compare those with the strain gauge as an additional correlation task. So if I go back to the single model view, instead of looking at the deformation, I can also look at the stresses. And so this is von Mises stress, and I will again show it like this because then you can clearly see the stress buildup at the mid section of the bridge deck, like this.